Hey everyone, and welcome to This Explainer. We are about to decode the mathematical engine that is literally driving modern tech. If you've ever looked at the totally wild advancements in artificial intelligence and data science and thought, how does this actually work? Well, you are in exactly the right place. Today, we're popping the hood and looking at the absolute foundation of the whole shebang.
Now, I completely get it. For a lot of us, just hearing the word statistics makes us want to run for the hills. It kind of conjures up these images of dense textbooks and endless boring equations. But let's scratch that right now. Mathematics, and specifically stats, isn't just a bunch of abstract numbers. It is literally the secret weapon that makes AI and machine learning predictions actually work. It's the superpower that lets us find hidden truths in total chaos. So here is our roadmap for today. We'll start with exactly why AI needs statistics, then move into understanding your data, cover the basics of descriptive stats, tackle the pesky outlier problem, and wrap up with inferential stats.
All right, diving right into Section 1, why AI needs statistics, going from messy data to powerful models.
We live in a world that is just overflowing with massive, chaotic, real-world information. Statistics is the scientific framework we use to take all that mess and turn it into reliable models. Without it, AI would just be guessing blindly in the dark. The core workflow here happens in 3 simple steps. Step 1, we collect the data, gather the raw facts and figures. Step 2, we mathematically describe and summarize it so our human brains can actually comprehend what we're looking at. And step 3, we train algorithms on that summarized data to make powerful predictions about the future. Pretty much every complex AI model you interact with is essentially executing a highly advanced version of these exact 3 steps.
Okay, moving to Section 2, understanding your data, the foundation of all our analysis. Before we can do any of the fancy math or run any sophisticated algorithms, we have to build our foundation. We absolutely need to understand how our variables are structured. Feeding the wrong type of data into an AI model is honestly like putting diesel in a gas car. It's going to break. Think about this incredibly simple counter question. If I just walk up and ask you, what is the age? Your natural, immediate response is going to be, well, of which person? This proves a really foundational rule. Data points, which we call variables, are totally dependent on individual subjects. The person is the anchor, and the variable, like their age or their salary, is the specific measurement tied directly to them.
Once we have those variables tied down, we have to classify them. Broadly speaking, we deal with 2 main types. First, quantitative data. This is your continuous, numeric stuff, things you can physically count or measure, like age, height, or salary. Then we have qualitative data. This is categorical. It puts individuals into distinct groups, like their gender or their favorite movie genre. Knowing this distinction is absolutely crucial because you analyze these 2 types using completely different mathematical rules.
Let's look at a quick example of that qualitative categorical data. Imagine a super basic frequency distribution table derived from a sample data set. We've got 3 categories of flowers: roses, lilies, and sunflowers. Next to them, we literally just count how many times each category pops up in our data. 3 roses, 4 lilies, 2 sunflowers. It is incredibly simple, right? But this exact structure is how we begin to mathematically summarize the real world. And here is how that builds visually. We take that exact frequency table and map it straight into a bar chart. Boom! Suddenly the data is instantly readable. You aren't scanning numbers anymore. Your eyes immediately tell you that lilies are the most frequent. This is step 1 in descriptive analysis, using visual plots to make data instantly comprehensible. Which brings us nicely to Section 3, descriptive stats, summarizing the past.
This is the phase of our roadmap where we start finding the mathematical heart of our data. We might have millions of rows, and we need measures of central tendency to figure out what that data is trying to tell us. The most famous baseline here is the mean. It's just your standard arithmetic average. You add up absolutely every single number in your dataset and divide by the total count. It's highly reliable, used all over machine learning, and gives you a fantastic starting point for finding your typical data point.
But the mean definitely isn't perfect, and that's exactly why we need the median. The median is the literal, exact middle value. To find it, you just sort all your data from smallest to largest and point to the number right in the center. If you have an even amount of numbers, you just average the middle 2. You are going to see why this second measurement is an absolute lifesaver in just a second. Rounding out our central tendency trio is the mode. This one is super straightforward. It's simply the single most frequently occurring element in your dataset. If you have a list of ages and more people are exactly 24 years old than any other age, then 24 is your mode. Together, the mean, median, and mode form the descriptive core of our entire analysis.
All right, section 4, the outlier problem, or what happens when bad data breaks your model.
So, what happens when our beautifully clean data gets invaded? Real-world data is almost never perfect. Sometimes a massive, wildly unexpected data point sneaks in and totally skews our math. Let's look at a concrete example. Imagine a perfectly clean, sorted dataset, gently ranging from 1 to 6. When we run our descriptive stats, everything looks great. Our mean is about 3.2, and our median is exactly 3. They align perfectly, giving us a really accurate picture of the center. But then, disaster strikes. Imagine a rogue number, a giant 100, just drops right into our gentle little dataset. Maybe it's a massive anomaly, or maybe someone just fat-fingered a couple of extra zeros on their keyboard. But now, this massive outlier has invaded. What does this do to our central tendency? Check out how our two different measurements react to this. The mean, because it physically has to add up every single number, including that giant 100, is completely distorted. It skyrockets to 12.0, which honestly doesn't represent our normal data at all. But look at the median. Because it only cares about physical position, the exact middle of the sorted list, it safely stays anchored right at 3.0. The median literally acts as an anchor to save our analysis from that outlier's distortion.
And that brings us to section 5, inferential stats, making predictions and seeing the future with probability.
Now that we've secured our baseline data, this is where the real magic happens. We're shifting gears from just describing the data we already have to making incredibly powerful predictions about the data we don't have. To understand why we need inferential stats, just look at this massive number, 8 billion. Let's say you're testing the safety of a brand new global vaccine. The planet has roughly 8 billion people. It is logistically, financially, and practically impossible to test every single person before releasing it. The scale is just way too big. So what's the solution? We rely on a sample size. Instead of 8 billion, we meticulously select a diverse, highly representative group of, say, 500 individuals. We can definitely afford to run tests and carefully monitor 500 people. But the million-dollar question is, how do we mathematically prove that what happens to these 500 will actually apply to the entire 8 billion? That's the exact difference between these two core concepts. Descriptive statistics, what we just did in the first half of this explainer, summarizes the known, collected data from our 500 people. Inferential statistics is the mathematical bridge. It uses advanced probability to take the results from that tiny sample and draw rock-solid predictive conclusions for the whole 8 billion person population. And how do we build that bridge? Through a process called hypothesis testing. First, we formulate an assumption, which we call the null hypothesis. Then, we run rigorous statistical tests on our sample data. Things like a t-test, a z-test, or a chi-square test. We check the resulting p-values to see if the math actually proves our assumption is statistically significant. Finally, we either accept or reject the hypothesis. This exact workflow is how an AI algorithm mathematically verifies that a recommended video will keep you watching, or how a data scientist proves that a specific demographic is highly likely to churn. And just like that, we've reached the end of our roadmap. Statistics is so much more than boring math on a chalkboard. It really is the ultimate science of making better, smarter, more predictable decisions in a completely chaotic world. It's the engine of AI. You now have the fundamental steps to decode this landscape. So my final question to you is, statistics isn't just math. It's the science of making better decisions. Are you ready to see the hidden patterns in your data? Keep exploring, keep learning, and thank you so much for joining me on this explainer.